So maybe we'll wait for like 4 more minutes and then we will start. Okay, so maybe we'll get started. Just let me. Mm, okay. Okay. Just a second. There's some issue with my tab. Oh, yeah, now it's connected. Sorry. I hope the screen is visible. The tab screen is visible. If not, let me know. Okay, thanks. So I think this is tutorial 7. All right. This is- So, hello, namaste, and welcome everyone. Welcome to this tutorial. Uh, This is week 7. So we will be discussing week 7 in today's tutorial. Uh, in particular, so each week, as you must have seen by now, has some a main theme to it. Okay, so for example, few weeks back, we were learning about something called principal component analysis. After that, we moved on to something called autoencoder. And in some sense, so you might be wondering that, okay, what is the direction? I mean, what are we? So whenever you see a course and whenever you are doing a course, there should be, you should always know that what is the flow of the course, right? So it should not be that, okay, you are thinking, okay, this week is something which is completely different to what was taught previous week and things like that. So right now, what we are doing is, in some sense, we are seeing at, the we are looking at different aspects of deep learning. Okay, so if I had to, say it formally, uh, okay, so we started with something called previous 2 weeks revolved around curse of dimensionality. Okay, in particular, we saw that, okay, dimension having large high dimensional inputs is not a good thing to have in general, and that is why we should look for ways to, reduce the dimensionality of the input itself. For this, what we saw was, something called PCA, and then we saw deep learning based dimensionality reduction method, which was autoencoders. Okay, so having said that, so this was one aspect of deep learning. When someone is solving some problem using deep learning, this is something that he should know. That this is something that he or she should know. Okay, so this was one aspect. So this week, okay, uh, this week, what we will be doing is something called bias variance trade-off. Okay, so okay, so let's discuss about it. Okay, so what exactly is bias variance trade-off? So the fundamental idea, in some sense of bias variance trade-off is that, for a given problem, for a given learning problem, the main question that someone asked was, okay, so let me write it down. A given for a given problem, are all models equally good? So this is the central question that bias variance trade-off tries to answer. Okay, so why is that? Well, so let us say that, so in general, okay, so okay, let me first tell you something, and then maybe I will come to what regularizations and all those things are. So let's say you already, so in general, we don't know what the real world problem is. Okay, so when we are given some data in real world, we don't know how that data looks like. Okay, we are clueless. Okay, so we don't know if it is linear, or is it quadratic, or is it sinusoidal, or periodic in some sense, or how it looks. Okay, so we are clueless about data. But for the sake of explanation, let's assume that, you knew that, okay, your data, well, it looks something like this. It looks something like this. It, maybe it is in a circular. It lies inside a circle. Okay. For the sake of simplicity, I'm just taking this example, but always remember that this might not be true. Okay. I mean, in general, the data can be weird. I mean, you cannot assume any shape on it. However, let's say we are given this data. Now someone comes and says that, okay, uh, so okay, okay, now someone gave you this data and you are asked to, okay, now fit a model to it. Okay, like, maybe do some linear regression, maybe use a deep learning, some deep learning network, or you know, do something and give me a prediction model. So what do we mean by prediction model? So let's say this is X and this is your Y, right? So basically, someone, so if you are asked to fit a model, basically the model should take as input X and predict Y. Okay. So you said, well, okay, fine. So you said that, okay, I will use something called, I will use linear model or linear regression. Okay. And you say that, okay, this looks like a linear regression problem, and what I will do is I will fit a line like this, right? Well, I mean, you can clearly see this model won't be good enough, right? I mean, this model doesn't a linear function can never approximate a circular function, so to say, right? Uh, Having said that, okay, then what would be something that will exactly fit it? Will a quadratic function fit it? So let's say that maybe you take a quadratic function, something like this. Would this fit it? Would this thing fit it? Well, doesn't look like it, right? I mean, it looks like, it is able to somehow cover this part of the circle. However, you want this entire circle, not just the boundary, but the inside interiors as well to be covered. Well, this will also not work, right? So, well, someone said that, okay, so also I mean, obviously you can see that since it is a circular simple model that will actually fit this, would be something like some r sine theta plus r cos theta kind of function, right? I mean, this is basically a coordinate of a circle. So this basically defines a circle, and hopefully, I mean, if you learn the r correctly, and maybe add some shift to it, some new shift to it, and you should be able to make appropriate predictions, right? So all models are not good. So that is the central answer, right? I mean, that is the main point. So the answer is no. Okay. So someone said, okay, so now we know that, okay, for a given problem, all models are not equally good. Well, then, uh, okay, now we know that all models are not equally good. So when the people basically struggled, that, okay, we know that all models are not good. So what model is good? Okay, I mean, how do I even come up with a model that actually how do I even come up with a model that will be good for my given problem? So for that particular to answer that particular question, people came up with this idea of bias variance trade-off, and bias variance trade-off uh, basically answers this question. Okay, I mean, it what it does is okay. So let me come to the main concept, right? Uh, okay. Right. So, okay. So let us look. So let us first solve one problem. Okay. So someone is trying to come in. Okay. Uh, yeah. I don't know. Okay. I don't know if I'm admitting someone. It is not able to come in. Maybe there is some issue. I don't know. Okay. So here is the claim. Okay, so I saw the lectures basically, and I felt that there are some gaps that might be required to fill in. So I am just using this lecture as an opportunity to explain those topics. But someone is not able to admit. I don't know why. Okay, so here is the claim. Um, the 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 optimal the optimal function g, maybe mute. Yeah. So okay, people are joining. Okay. So the optimal function g that reduces that reduces expected value of g of x minus y whole square is uh, g of x equal to expected value of y given x. So I hope you are familiar with the concepts of expectation and conditional expectation. So what is this thing? So this is integral of y p of y given x dx dy. Okay. Some this integral will be over y. So this is one claim. Maybe if time permits, I will prove this in the end. But this is uh, this is one claim. Okay, so I'm not proving it, but maybe you should know this that if so given a data set, okay, the optimal classifier or optimal function that reduces this given loss function is this conditional expectation itself. So why is this a function of x? Well, this is a function of x because this conditional expectation is actually expectation of y given x equal to small x. Capital X is the random variable, small x is the instantiation of that random variable, right? So, so this function will is the optimal function that reduces uh, this this particular loss function. Okay, so I hope so. I am not proving it right now. If time permits, in the end, maybe I will prove it. If not, maybe we can also take this in the next tutorial. But this is a claim. So just maybe for the time being, take it take my words and just believe it. Okay. So okay, now so this is a great result, right? I mean, uh, so now when you are given a data, you can say that okay, this is the optimal classifier. I know this. Okay, so maybe I should use this function, right? G of x. This is what I should be using, right? Well, there is a catch here. Okay, this the catch is that this g of x, which is equal to this thing, requires you to evaluate this integral, right? Now, this integral requires you to know this py given x, right? Now, py given x is something that depends on the data, right? I mean, we are given the data, but we don't know the exact density or distribution on it, right? So this thing is not known to us. Okay, basically, if someone gives you the data, you don't know what is the this distribution. Okay, I mean you can estimate it and things like that, but the estimate would again be bad. Things like that will come in, and hence this is not something that you can exactly calculate. Okay, so the catch here is py given x is not known, right? So so what is the condition that we are in right now? So we know that okay, g of x, which is this thing, is the optimal model for to reduce this loss function. Okay. However, the problem with it is even though we know this is the optimal classifier or optimal model, we cannot calculate it because this density is not known to us. So this is the situation right now. Well, then someone can say that, okay, fine, we don't know the optimal thing, but is it possible to, maybe come up with something which is close to this? Is it possible to do that? So to do this, people basically what people did was, so how does one quantify that if a model g of x is close to this this loss this optimal model? How does one how would someone know that? So one way to uh, basically tell this or maybe establish that concept is, okay, so let me write it down. How uh, Okay, so the question is, we need something which is close to Let me call this G star, okay? G star of X, which is equal to this thing, expected value of Y given X is equal to small x. Okay? We need something like this. But then the question is, do we quantify, how do we quantify closeness? So I hope you are getting my point. So these are the layers of this question. Okay, so someone asked you this big question, right? And now you are basically breaking it down into thin layers. So these are the, I mean, from a research perspective, this is how research happens. Right? You have a big problem, you see some aspect of it, keep asking question and answering them, and eventually maybe you get something which is acceptable to society. Okay, so so how do we define this closeness? Okay, so uh, so one way to do this is that, okay, uh, this is where the concept of bias comes. Okay, well, not exactly, but let me just say it nonetheless. So bias is something which does this. Okay, just to make it clear, bias is something that does this. So I in your notes I saw this, so I'm using those notations so that you can relate it with it. So so bias of a model f hat of x. Okay, so f hat of x is a model. Okay, f hat of x is equal to expected value of f hat of x. Okay, minus f of x. So this is a uh, uh, so how is it defining this closeness? Okay. Uh, well, let us see. So this is your, so okay. So maybe I should not use exactly the same notation. So let me write it like G star of x. Okay. So this is your optimal classifier, right? I mean, this is what G star is. This is your optimal classifier. Now, this is your average, so let's say this, your f hat of x was, let's say, uh, let's say it was something like, linear model. So, for example, let's say f hat here was linear models. What does linear model mean? It had some form like, W transpose X plus B time. Okay, this was the form of it. So I mean, it can have different W and B's. Okay, fine. But I am saying that, okay, take all the possible linear models that you can have. Okay, so what do I mean by all the different models? So you have a data, you train multiple instances of your model on this data. You will have several linear models now, and you take the average of these models. So give x as input to all these models, take average of them. Okay, so this will be your average prediction in some sense. Okay, and this is the true prediction. Okay, optimal prediction in some sense. Now what this is saying is that how far is my average prediction from the optimal prediction, right? So what is it say? Bias, what is it describing? How far is the average prediction from the optimal prediction, right? So this is what bias is telling us, right? So so in some sense it is, trying to define what this closeness is. Okay, I mean, so I hope you can see that. I mean, if this is not clear to you, maybe you can just ask questions, but so I hope I'm able to convince you that, quantifying closeness is done by something called bias of the model. Okay. Well, having said that, uh, now next question that someone might ask you is that, okay, so is bias enough? Okay, is can is defining the bias, and is the concept of bias enough to for our original question? Where was it? Yeah, so this was our original question, right? So that for a given model, are all models good? We said no. Okay, then we got our original. So we got our optimal model that is optimal. You cannot do better than this. But the problem is that you cannot calculate it directly, because there is something that you don't know. Well, then you said that, okay, so can I come close to this function, the optimal function? Well, then you had to define your closeness, and then you define something called bias and said that, okay, this is something that maybe defines what you need. Okay, so to say, closeness between your model and the optimal model. Well, this is fine. Are we done? Well, let us look at this example, right? So this model, this data was something like, so this was like circle, okay, a closed circle. And the model that you said was this, okay. Maybe you fitted it another time, you got another function like this. Maybe you again fitted it, it got something like this, okay. So what is bias? So let's say at this point, so let's say at this point, the model function was not defined, okay. Sorry. So I need to, okay, so maybe this is the function. This is your, so maybe just let me just draw just one linear model. Otherwise it gets cluttered. Okay. So maybe at this point, at this, for this X, okay, this was the prediction of the model. Of all the models, it was close to it. And this was the prediction. So this was the actual prediction. So this is the error, right? Okay, fine. Now maybe you are done, right? Right? I mean, maybe you might think that having defined my bias, you are done with. Okay. However, I mean, that is not the case. For example, let us see this another example. Okay. So I think something like this would do. So let's say this is your new data. Okay. So it's like a sinusoid, but it's not on x-axis. It's on some other line. Okay. So this is your model. Okay. Now, okay, so this is, okay, maybe I should have added some noisy data, noisy points as well. So this is there are some noise as well to it. Okay, so there's something like this would also suffice. Yeah. So this is our data. Okay, so uh, maybe my drawing is not good, but yeah, I hope you get the gist of it. So this is your data. Okay. Now, again, you tried with a linear model. So you fitted your linear model a lot of time. So maybe this was the first model that you got. Maybe you got another this model the second time, third model this third time, things like that. But every time, let's say if I look at this point, this particular point, so this is the point, let's say X. All the models are giving something which is in this range, whereas the actual value lies here, right? Yeah, so I mean, the actual value lies here. So I mean, it is very far, you can see, right? So obviously, this linear model has a high bias, right? I hope you can see that. Well, now let's say that, okay, you say that, okay, well, since I can see that this linear model can never approximate such a function, what if I use a complex model? Maybe, let's say, what if I use a, quadratic or polynomial function, which has, higher degrees. Well, fine. Then, so okay, you said that I will use a very high degree polynomial function, maybe of the order of x raised to 100. Okay, and you fitted it. Okay, okay. So now, what the model did was something like this. So this was your data, right? So it said that, okay, since you were reducing your training error, it looks something like this. Okay. So basically, what the model did was it captured all the points in your data. Okay, this. This is how your function now looks like. So, okay, I hope you are following me. If something is not clear, please ask questions. Okay. So Yeah, so this was the data. You saw that linear models are not good. Let me also write it down. Linear models, linear models, not good. Why they are not good? They have high bias. Okay, so high bias. I hope you by now you know what high bias is. Okay, why high bias? Because this difference, right? This difference was too high for all x, and hence at each point the distance was high. So this was the distance here. This was the distance here. Oh, sorry. This was the distance here. This was the distance here. This was the distance here. Something like that. Okay, so I hope you can see that, right? So this was again the distance. So at all these points, the difference between the average output and actual output was high, so it has a high bias. The difference is large. Hence, it is not a good model. So you said that okay. Now what I will do is I will take a complex model, which is very complex. It is of the order. It is a polynomial model with a degree 100. Okay. Well, now if you have a degree 100 polynomial, I mean, what it did was it actually traced your data exactly as it is. Right? So this is how your model basically did. Okay. Well, now, okay. So now what happens is and you use this model and you deployed it in real life. Okay. Now what happens is that in real time, a model like this comes here. Okay. So this is the data point that you have to predict your value for. Okay. Well, it says that okay for this particular x, I will give something which is here. Okay, I hope you can see that this is the actual point that you want to predict the value for. And since your model says, okay, so I mean, for this x particular x, your model what it predicts is something like this. Okay, however, you can see that okay, the actual value was something like here. Okay, so again, you are incurring some error. Why is this error exactly coming? Well, this error is coming because you used a very complex model. Uh, I hope I'm able to convince you with this point. If not, let me know. So what I'm saying is that this was the x, right, for which you had to predict. The model is this. So this is the pink colored line is the actual model that you have learned. So what is the value that it will predict? This is your predicted value, so y hat. However, for this point, the actual predicted, so the true value is y, and hence this is the error that you are incurring. So again, you are incurring a lot of error. I mean, in this related to this diagram, it is a lot of error. Okay. Well, now you are again upset. Okay, why I used a very complex model as desired. I mean, using a simple model was not working out, so the linear models were not working out. So I used a very complex model, and something like this was fed. And during training, you even observed that okay, the training error decreased, and you were able to you were able to get almost zero training error. However, when you are actually deploying it in real life, you are again observing that your customers are not happy with you because it is giving some bullshit out. Well, the reason for this is because you used a very high, very complex model. Okay, and because of it, instead of learning the model, instead of learning some prediction rule from the model, what it actually did was it actually memorized the data itself. So, maybe I will write it down. So, uh, complex model, complex model. Instead, instead of learning something, okay, learning something. What it actually did was it memorized the data. Okay. So this is again not good, right? I mean, you want to learn something from data. You don't want to memorize the data. If you had to memorize the data, I mean, machine learning and all those things would not be required. You can just, make a hash table or something like that and just be done with. So this is the issue with using very complex models as well. So the gist of the story is that, you cannot use very simple models like linear models. neither can you use very complex models. Okay, both of them have their own disadvantages. Linear models don't fit good. Complex model, fit overly good, and hence they don't learn anything, and they are able to just memorize the. Well, for so so obviously bias is something which is not good in this case, right? Bias is not something which will be able to characterize this behavior, right? This behavior that is shown by this pink colored line. So for that, what we have to define is something called variance. Okay, so what is the variance? Variance of a model f hat of x is, uh, I hope I'm writing it correctly from this. Yeah, it is expected value of f hat of x minus expected value of f hat of x. Okay, the whole square of it. Yeah. This. Okay, so this is the variance. I mean, someone can now you can ask that, okay, why should variance help us in characterizing this behavior that we saw here? Well, what is this variance telling you? This is telling you that, I mean, roughly speaking, it tells you that how much different f hat of x, okay, when again you take your model and train it multiple times. Okay, every time you will get a different pink line. So this is something like this. Maybe there is another function that got something like this. Okay, something like this, right? So you train multiple instances of it, get different models. Now how much are these models deviating amongst themselves? Okay, in some sense, so let's say your model, next time your model does something like this. Okay, it's even more noisy. Okay, again you train it another time, you get something like this. Okay, which is again maybe very different from what you had earlier. So variance is trying to capture the fact that if you train your model multiple times on the same data, how much different each of these models are going to be, right? So this is your f hat of x, your one instance of model. So this is one instance of model, and this is your average model. So basically, suppose you have trained it multiple times, so you have multiple models, okay, trained on the same data. Take average of this model. This is what the second term is. The first term is one instance of that model. Now how far is one instance of this model from the average model? Okay, this is what the variance is trying to capture, right? So I hope you will agree that if a model has high variance, okay, if a model has high variance, it will fluctuate a lot. Okay, mean so coming to it, high variance in high variance, roughly, let me also quote it. Okay, roughly, uh, what it means is how much your model fluctuates. This is what the variance is telling you. Okay, so having said that, when bias told you how far you are from the optimal model, okay. Now variance is telling you that, okay, uh, well, how much your model is fluctuating, okay. I mean, maybe you could. So, with the case of linear models, was there a lot of fluctuation? Well, no, right? I mean, the linear models were like, okay, they were not able to fit the data appropriately, but they were not fluctuating a lot. However, this new thing that we came up with, though it is fitting the data, but it fluctuates a lot. So we need something which has. So let me draw something like this. Okay. So let me draw a graph. Okay. So this is something called complexity, and this is something called error. let me, so now I haven't explained you what complexity is. By now you might have understood, by complexity what I mean is that linear models like here, they have low complexity, right? They are simple models, just one parameter, so just two parameters w and b. Whereas this x raised to 100 polynomial has 100 parameters, right? And hence it is a more complex model. That is how we are trying to quantify the complexity, right? So let us try to uh, yeah, let us try to maybe show that. Okay, let me try to. So how will the training graph for linear models look like? So maybe for linear models, the complexity is low, right? So low complexity region would be something like here, would be somewhere here. Okay, so let's say this is the complexity of linear models. But with since the error was very high, it should be something somewhere here, right? So for something which has low, I hope I'm able to convey what I'm trying to say, right? So for a linear model, the complexity is low and hence the error is very high for this case, for this particular case, right? So, okay. However, for this x raised to 100 model, right? It had a high complexity, right? It had a high complexity. However, and the error that we saw was on training set. Okay, the error on training set was also low. So this was here something here, right? So I hope you are able to you will agree with me that this is so. Let me write it down. So I hope you will agree that this region of the map of this graph, okay, this region of this graph is what should have uh, uh, so we saw that for linear models, it has high bias, right? So it has high bias, okay, right? So what do we mean by high bias? This is exactly what we saw here, right? In this model, that multiple instances of linear network, but they are not even close to the what we actually want. So this difference is high, and hence since this difference is high, the bias is high. Okay, so this is high bias region, and as we go there, I mean, hopefully the bias, so this is high bias, then this should be the low bias region, right? I mean, just by common sense that if this is a high bias region, maybe increasing your complexity should reduce the bias. But with this x raised to 100 model, what we saw that it had a high complexity, but it also had high variance, right? It was fluctuating a lot. So it has high so basically this part of the area, so this part of this graph is actually high variance, right? High variance. And hence, since this is high variance, as you go here, hopefully it should have low variance, right? So can we see this? So with the linear model, I hope I have convinced you that linear models had what? High bias, right? But do they have do they have low variance? I mean, intuitively speaking, you could see that this is the first model, this is the second model, this is the third model, fourth model. So these models are not fluctuating a lot, right? I mean, they are just so this is a line, maybe it is perturbing a bit, something like this, but it is still there, right? I mean, it is not varying. So it is not like if this is the model, the next time I train it, it becomes something like this. This is not happening. It is just perturb. It is just maybe someone is perturbing it by slightly. So I hope you will agree that the one instance of the model is very close to the average model, right? So if you perturb by some little amount and take the average, I mean, I hopefully each of the model are very close to that average model. Hence, we can actually see that linear models do have low variance, right? At the same time, we saw that hopefully I convinced you that this x raised to 100 model had high variance. But does it have low bias? Well, by going by the definition of this bias, this thing, right? I mean, we can see that, okay, an average prediction of the model is somewhere here. I mean, since it is actually memorizing the data, at each point it is exactly able to do what it is asked to do. However, and even the optimal model, whatever would be something like this, right? Something like this. So it is the predictions are close by, right? So variance, I mean, with more complex model, I mean, you can see that it has also has low bias. I mean, if so, I hope I was able to convince that, this. So I mean, maybe the optimal thing was something like this, right? And you took this point, and this was your prediction, and this was the optimal thing, so it was close by, right? So this something like this, right? So I mean, hopefully the bias was very low. So yeah, I mean, we can see that this complex models do have low bias and high variance, whereas very simple models have high bias and low variance, right? uh, maybe I was able to convince you. I don't know if I was able to convince you or not. I mean, if there is some doubt, please open up and ask questions, because I don't know anything. I mean, I don't know if I teach good or bad. Okay, but this is something which is important, and if it is not clear to you, maybe you should ask questions and get it clear, just to be on the safe side. So let me draw that thing again.
Can you please, hello?
Yeah, yeah,
Yeah, for low bias, how the
yeah,
variance is high? Can you please come again once again, please?
yeah, yeah, sure. So, so bias and variance are not related to each other. Okay, it is not that low bias tells. So it is not that low bias tells us that it is high variance. Okay, is that clear? That why? Well, why? Because this particular thing is not related to this thing at all. Okay. I hope I'm able to convince. So I hope you are able to see that, this thing and this thing are not related to each other at all. So low bias doesn't imply that it will have high bias. This is something that we are observing here. Okay, this is just an observation. Maybe if I change this x-axis to something else, because we are using complexity as this axis, maybe because of that, it is coming out naturally that, okay, yeah, we are able to observe that low bias region also corresponds to high variance regions, and high bias regions are corresponding to low variance region. Okay, this is something that we are observing, but bias and variance as such are not related to each other. Okay,
So that
but
statement true for all cases, right, Piyush?
yeah, yeah. Sorry, can you repeat your question?
So whatever, I mean, as they are not related to each other, we
Yeah,
cannot generalize that low bias means high variance and high bias means low variance, right?
yeah. We cannot say that. We cannot say that. Okay.
Okay.
It is just that on this graph, okay, in this particular graph that I have made, it turns out that these two regions are, corresponding to the same thing. So this is again a very vague thing. Okay. I mean, this is just for explanation, but you are exactly correct that low bias doesn't imply high variance, and high bias doesn't imply low variance. Okay. But when if you think of it from a complexity point of view, okay, so if a model has low complexity, it is a simple model, right? A simple model would definitely have high bias, depending on the data, of course. Or I mean, if I actually change the data, I can show you that. Okay, so let me say, maybe what I will do is do something like this. Okay. So let us say that this is your data. Now I'm changing my data. Okay. So maybe this is your data. Okay. Now you say that, okay, I am going to use a simple model again, right? So this is your simple model, which is your linear model. Okay. So now it's all of a sudden, right? this linear model, which in this case was looking to be very bad, looks very good now, right? Because it is able to exactly capture the linear relationship between the data points, and it is perfect. So, well, in this case, is it high bias? I mean, for this data, we saw that for this particular data, we saw that okay, the linear model were high bias models. But for this data, for this new data, is it high bias? Well, I mean, no, right? I mean, now it is very close to the predictions. So let's say this is the first model, third model, and you train it multiple times, and then you will more or less get the same model, right? So this time you have something, you have a model, okay, this model, which has its prediction, which are very close to the actual outputs, right? This is your, so if you sum all these all these errors, this is what your bias is, right? Well, now my bias is, so it's not so it's not a high bias model anymore, right? Is it high variance? Well, it is not high variance either, right? I mean, now the models are not fluctuating a lot. It is just so each instance of the model is very close to the average instance. So maybe, so these are multiple models, okay, you took average of them, and maybe the average came something like this, okay. So this line, this red line, and this okay, so both of them are red. So however, this lightened line is close to the dark red line, right? So this will be the case with where you have low bias as well as low variance, okay, right? I mean, so I hope you can see that low bias didn't imply that this is high variance model, right? Is my are my thoughts clear, or maybe I
Yes.
missed
Yeah.
something,
Yes. Yes.
right?
Thank.
Yeah, yeah. So thank you for asking question, by the way. Really encourage it. Okay, so yeah, so this is the big picture, right? I hope so. That was a good question. Generally, people confuse themselves by making themselves believe that high bias implies, high bias implies low variance, and low bias implies high variance. Well, that is not the case. Okay, these, okay, whenever, so bias and variance are just fancy terms for these particular expressions. Okay, these two expressions have nothing to do with each other. They are independent. Okay, it's just that when we think of it from a complexity point of view, they, I mean, high bias and low variance regions seem to be the same region, and low bias high variance regions seem to be the same region, and things like that. However, they don't imply anything. Okay, so there is no relation between bias and variance. Okay, just to be, I mean, okay, I won't confuse you, but yeah, there is no
Hi Piyush, could you also explain the total error and how variance plus bias square plus
yeah.
like those
Hmm.
unreducible error correspond to total error, like for the sake of completeness, right? For this topic.
Okay, so okay, so let me complete this. So do you want? Okay, so maybe let me ask you. So do you want me to solve the this week's question or not? Because if I go into that, then maybe I won't be able to take up the questions.
No,
That
no.
is a good thing.
This week's questions are important, so let's just keep that. Yeah, maybe
Yeah. So
later.
maybe, yeah, yeah, maybe later. Okay. But it is a good exercise to actually prove that the total error is actually. So maybe I will write it down. Okay, fine. Okay, so maybe. So this is something that was, I don't know if it is there in lectures or not, but total error is nothing but bias square plus variance plus uh, plus some noise. With this is not reducible. Okay. Maybe if I get a chance, I will prove it. Otherwise, maybe so maybe let's see how it goes. If I am able to get time, I will. So I mean, so that is why I was hesitating to say those things. But okay, now you can see that there is actually some relation between these three terms. Okay, total error, bias, and variance are actually related in this way. However, I mean, it depends upon total error as well, and I mean, it is data specific and things like that. So I won't complicate things. Okay, similar equation. Okay. So okay, so is there proof for it? Not. I don't know. Because
Uh, Actually,
I
no, don't need proof. Just the intuition would be sufficient, I guess, right? Just basic some explanation, not the proof.
okay. So I will just quickly do some maths. Okay. So Mona has raised hand.
Yes, I just
Any
wanted
question?
to ask, how
Yeah.
important are these, proofs? Because for me, it sort of gets me off track if I'm seeing a lot of proofs, and a lot of times in the lecture, what is happening is that there are a lot of proofs, and it
Mhm.
becomes very mathematical, and the whole crux is lost. So, how
Lost. Yeah.
important are those proofs?
So proofs are important if your course so if you are working in a domain which is bit research oriented. Okay. So I agree that sometimes when there are a lot of proofs, we get lost in the middle of it, and we are not able to see the big picture. But yeah, I mean, if you are a person who is not involved in uh, uh, research or academics per se, then maybe proofs are not that important to you. But I mean, for example, people in industry, I mean, they are never going to use these proofs. I am sure about that. Okay, what they are going to need is something which is very superficial, and they don't need to learn all those things. They don't need to see the proof for that. However, if you are in an academic line or maybe a research line, then these proofs are somewhat important, and I mean they will help you to construct your theory or things like that. So does that answer your question?
Yeah, that's fine, thank you. But what I have felt is that,
Mhm.
in the lecture, sometimes they don't really help in correctly answering the assignments. And additional material is required to actually understand, the topics with respect to what is asked in the assignments. Because initially, with so many lectures, you kind of get, because I have done a few others also in NPTEL, the material
Yes.
was sufficient, the lectures, but now I'm not feeling that. So that's why I asked this, like from the assignment perspective also. I feel that the lectures are getting more mathematical and not helping correctly. Ultimately, we need correct, good marks also. So
Yes.
I have now, also relying a lot on other additional material.
Right. So, from my experience, let me tell you my experience. My experience has been that NPTEL, for this course particularly, the materials, so the lectures are very involved and mathematical. I agree with you. They are also in, so there are, sometimes they also try to give some visual intuitions to you. Okay. But in the assignments, the main idea is, have you understood the big picture or not? Okay. So, so what you were saying that, okay, seeing all those mathematics and things like that, it is true that, we often get lost in it, and, we are just seeing that, okay, is this equation correct or not? Or that equation doesn't seem to be correct. How is this assumption coming and things like that? And these kinds of thing, actually might deviate you from the big picture. However, I think the way to see these lectures would be to just remember the end goal that is promised to us. Okay. Or maybe so it's like, so there is some proof and some theorem. Okay. If you are not comfortable with the proof, maybe skip it. Okay. But after you skip it, just see what is the final message of that theorem or particular thing, right? I think, I mean, I am myself doing some courses here at ISC which are very mathematical and involved. And because of that, but one thing that professors keep saying is that, focus on the big picture. They say that mathematics is something that, people can do. That is not a big deal. People can do mathematics, and that is not a big deal. Okay, and that is true actually. Once you are you get hang of it, mathematics will be something that you will say that okay, we will get to some maths, but what is the big picture that we are trying to see? So whenever you see some research paper and things like that, right? So uh, uh, they don't uh, they don't they don't put the proof in the main text. They will refer you to the appendix of the research paper, and the main context won't involve any proof as such. So I think the way to see the lectures is that keep in mind what is the big picture. I hope the professors do tell in the lectures. I hope that okay, this is the big picture that we are trying to see. And if they go to some theorem and maths, maybe if you are not comfortable with it, skip it and see the end goal of that theorem proof or whatever that mathematical analysis was, and then correlate it with the big picture that the professor has had promised. Okay, maybe that will be the I mean, that is how I do it. Okay, so it happens a lot of time that I am not able to understand what is going in the class, but I remember what the big picture the professor had told us. And if I don't understand, I ask question that okay, you said this, but what is the what is you said you proved all this theorem and things like that. How is it related with the big picture? So maybe that is how you should proceed, perhaps.
Okay, thank you. I'll try that strategy.
Yeah. Yeah. So someone was asking. Okay, so maybe we have diverted a bit. Okay. This thing, I will prove it in some time. Okay. Let me complete my chain of thoughts that I was trying to put it here. Okay. Okay. So, uh, yeah. So maybe I will just copy and paste this thing. Okay. Copy it. Okay. Also need to push these things up. Okay. Yeah. So now, so okay, so I hope I have convinced you that this is high bias, low variance region. This is low bias, high variance region. Okay. Now, coming to my point. So this is the punch point. Okay. So the way I understood bias variance trade-off and why is it useful to us is by this thing. Okay. Uh, take it a bit down. Yeah. So let us. So how do we, so, okay, fine. This is high bias, low variance region. This is low bias, high variance region. How does it help to us? Okay. So now consider, so a high bias. So, okay, let me ask this question. So maybe, I don't know, maybe I will put my thoughts here. Okay. So we saw that high bias for a data set, a high bias model always gives you high error. Will you agree with me on that? Why? Because if a model has high bias, that means that this thing is high, right? And what does this mean? That this it means that from you are very far, your model is very far from the optimal model. Okay, that is what it says. So if a model has high bias, it will also have high uh, error. Okay, I hope you will agree with me on that. As we saw with the linear model, right? So it will have a high error as well. If a model has high variance, it will have a low error, right? I mean, this model, that this pink model that we saw here, this has very less error, right? It is exactly giving you it is giving you actually zero error, exactly what you want, right? But remember, this is on the data set itself, okay? So whatever I am writing right now is on the data set, okay? So this was your high bias error. With as your variance increases, I hope you will agree that you will have very less error, as you saw, because your training data will you are actually memorizing your training data, and hence your training loss or training error will be very low, right? So if I try to complete this graph from this point to this point, How will it look like? It will look something like this, right? I mean, I hope you will agree with me on that. If not, let me know that you don't agree. Okay, it is not coming good. Yeah, something. Okay, something like this. Right? I mean, it will go on. It will go on and maybe become even zero sometime. Okay. So I hope you will agree with me that this is how training error would look like, right? This is your training error. Now, but so what was the problem with high variance model, right? The problem was it was not able to generalize well. Okay, so if I gave it a point, let's say, which was so this green example, right? I gave it a point this, it was giving me this, and I mean, this was the error. The problem with it was that this is your so as I the if you remember, this is how I drew my data, right? Something like this. Okay, sorry, something like this. And I deliberately added some noise to show you that just memorizing the training data is not good. So what was the error? What was the drawback of such a model, the pink model that we do? Because it was very high complexity, it was not able to generalize on test points. Okay, so the main idea is that, so given this such a model, how will the test how will the test error vary? This is the training error, and I think we all agree that this is how it will look like. But how will the test error look like? Okay, or test error or validation error, whatever you want to call it. So how would that error look like? Okay, so okay, now we know that for high bias models, the error is high and the model is not good. Okay, I mean we were trying to fit a complicated looking function with a linear model, so obviously it won't be good. So I hopefully I mean I hope you will agree that in this model, so these are the linear lines, right? If I give it a test point, let's say this point, again the error will be very high, right? I mean high bias will have high training error as well as high test error, right? So this is so I mean if I use a green color, I hope you will agree that again, I mean it will have a high test error as well, right? What was the case with high variance models? So this pink model that we saw, this thing, right? So something like this. The test error for these models was also high, right? That this is what we saw, right? So I hope you will agree that with high variance also you will get high error, right? Or maybe not that high, but I mean something like this. Okay, something like this. What would be the intermediate behavior? So, so the hype. I mean, this is what people observe also. But I mean, okay. So let me just make it like this. So this is how the test error would look like, right? Okay. This is the test error. Okay. So, so what we are able to see is that as I increase my complexity, so this area, right? Though my training error is low, but my testing error is still high. If I take a high bias model like this part of the region, low complexity models, my training error is high as well as my test error is also high. Both of them are not desired. What is desired is this sweet spot, right? This is what I think people have called it. So this is the sweet spot where both your training error is low as well as your test error is low. Okay, this is what we would like to have. Okay, so let me write it down. So this is your, let me call it sweet spot. So I don't know if I was clear or not, but I mean I hope I was clear that both these regions are not good for us. I mean end of the day I am going to deploy my model in real world, hence I want something which has low test error, right? I don't want it to have low training error I can make low by just memorizing the data. What is big thing in it? What I actually want is on unseen data, am I able to predict in a good am I able to predict a good Am I able to predict in a better way on test data or not? So this is what the region. So this is the region that I want to actually come up. Well, I hope I have convinced you. So this is the area that I would like to be in. Okay, but how do I even know? Because complexity is something that it is easier to define in polynomial models. But for, let's say, for a neural network, how do I even define complexity? There is no formal way to define complexity, right? So here is the idea. Okay, the idea is that, okay, so I hope you can see that high bias has some relation with low complexity, okay, and low bias has some relation with high complexity, okay. Now, would you agree that if I start from a high variance region, okay, hear me out. If I start from a high variance region, okay, that means if I start from this region, okay, and I keep increasing, and I increase the bias of the model, okay, I move in this direction, okay. Would you agree that hopefully I will reach this area? I mean, I don't know if I was clear or not. What I'm saying is that start from a high bias area, high bias region, which is this region. Okay, now increase the bias of your model. Okay, increase the bias of your model. So I mean, as we said that this is low bias, this is high bias, this is what it is. If you want to lower your bias, lower your bias, this is the direction that you will travel. However, if you want to increase your bias, this is the opposite direction is what you will travel. Okay, so from this region, which is high variance region, you start from this region and keep increasing the bias of your model. I hope you will agree that you will keep moving to the left side of this graph, and eventually you should be able to come up to this region, which is your sweet spot. Okay, Saket, you have some question?
Yeah, so this is where you're actually conceptually explaining regularization in a way, right?
Hmm.
Adding noise, some
Right.
sort of, and then perfect.
Yeah.
I never thought in this, connected these two things together. Very well described. Thank you. Yeah.
Yeah. Okay. Thanks. Yeah. So thank you for that. So I hope I am able to make myself clear that start from a high variance region, keep increasing your bias, okay, and as you keep increasing your bias, you will move to the left side of the curve, and hopefully you will be able to hit the sweet spot. And this is exactly what regularization is, okay. So what is the idea? Let me write down the idea. The idea is start from high variance model, okay. So let's say you start with x raised to 100, a polynomial which has a high degree, okay. Then the second step is increase the bias, okay. Now now as I was able to say, as I was saying that high bias somehow corresponds to low complexity, right, and low bias somehow corresponds to high complexity. So, given this relation, what does increasing my bias mean? Increasing my bias, moving in this direction, means that in the complexity axis, I am reducing my complexity, right? Right? I mean, I hope you will agree with me that moving from this direction to this direction, I'm not just increasing my bias, I am also decreasing my complexity of the model, right? So the next point that I will add here is this this is equivalent to increasing the complexity of your model. Okay, so let's say that so this is where formalism again comes in. So let's say I define, so if given a function f, so let's say this is how I define my complexity, some notation, okay, omega
Should
of
it
f
not
is
be
how.
decreasing complexity? Because we're
Sorry.
moving towards the left, should it not be decreasing complexity of the model?
Oh, sorry. Oh, blunder. Sorry. Okay, sorry. If I had an option to retract my statement, I would. So this is decreasing. Oh, thanks for correcting me, Mona. Okay. Okay. Sorry for the thing. Sakib, do you still have any question? Because you have raised your
No,
hand.
no, no, no. I'm sorry. I
Okay.
think I didn't lower it. Sorry. Yeah, my
Yeah.
question was answered. Thanks.
Yeah. Okay, fine. Oh, so sorry. I just said something which was wrong. So this is equivalent to decreasing the complexity of a model. So if I represent my model complexity with omega of f, this is the omega symbol, capital omega. So what I'm saying is, so this is a simple thing, right? At least visually you can see that this is where you start. Now lower your complexity. Okay. Now this is what you hit. So this is, so you are able to hit the sweet spot now, right? And so, what would it mean? Just let me just give you some example. Okay. So let's say you had a high variance model. So one example of high variance model that we saw just above was, this polynomial with degree 100, right? So let me write down a polynomial 100, a polynomial with degree 100. So let's say a100 x raised to 100, okay, plus a99 x raised to 99 plus dot till a1 x plus a naught. I hope you will agree this is a very high variance. I mean, at least that is what we discussed. Okay, in the context of our discussion, this is a high variance model. Okay, so as I said, we are in this region now. Okay, high variance, low bias region, right? Now I am increasing my bias. Okay, so what is one way to increase the bias of my model? Maybe what I will do is that, so would you agree with me that if a100, if I make a100 equal to a99 equal to, let's say, a98 equal to till let's say uh, maybe a20 to be 0, okay, my function eventually would become what? Maybe a21. Okay, what would my function, this function that I wrote here, what would it eventually become? So the coefficients from 21 till 100 are now 0, right? What, so what has it become now? It is a20. Okay, a21 is 0, so terms after this are all 0. A20 x raised to 20, a19 x raised to 90 plus till a1x plus a0, right? So as soon as I do this thing, right, this particular thing, as soon as I do this, I am moving from this region to, I am like decreasing the complexity of my model. Okay. So are you able to, maybe understand what I mean by, decreasing the complexity of the model? What I did was I started with a complex model, and what I did was, I just zeroed out few of the coefficients. That was equivalent to reducing my complexity of the model. Okay. So this was just to give you an example that, just saying that start from here and go here doesn't make any sense. I need maybe this example made it clear what I mean by, decreasing the complexity starting with from some point and things like that. The next point is, this is this is precisely what regularization 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 does. Isn't this exactly what regularization does? So what is regularization? I hope you saw the lectures, and I don't have time to explain all of it. But here is the idea. So you take your loss function. So let's say you have a classification loss or something like that. Okay, and it has two components. This was your origin. I think it is something called L tilde is what is denoted in the text in the slides, if I remember correctly. So let's say L tilde. So L is your original loss function that you have used. Okay, you would have used. Okay, What regularization says is that, okay, use this loss function, but also add another component to it, and which is this thing, the complexity of your model. So it is saying that, okay, reduce the loss function. That is what is desired. I want my loss function to be reduced. However, I also want my complexity to be minimal. Well, for this to make sense, you need to start from this region, right? I mean, if you start from this region and you say that, okay, now I want to reduce my complexity, you will never hit this sweet spot. So there is an inherent assumption that you are starting from a complex model. Okay, you are starting from a complex model. You are reducing its, you are steadily reducing its complexity. How you are reducing its complexity? Using this term. Okay, and you're simultaneously you are also decreasing your actual loss function that it was desired. Maybe it was, if it was a classification task, you are also reducing your cross entropy loss, but maybe you are also reducing your there is also a regularization term which actually tells you to reduce the complexity of your model. Okay, so so okay, so again, so just Mona was asking something that, I just so that you don't get lost in all these things. And what was the big picture? The big question that I promised to answer was that, okay, for a given problem, are all models equally good? Well, no, but we know what is the optimal model. Unfortunately, we cannot calculate it because, ty given x is not known to us. So bad for us. Then we came up with some trickery. We came up with some terms like bias and variance, which actually helped us to, make sense of what models are. How do I quantify if a model is good? How do I quantify if a model is very uh, uh, it if it fluctuates a lot, if it is close to my optimal classifier or not, and things like that. Using these concepts, we made a graph. Okay, we try to analyze that. Okay, how do these terms actually correspond to my how these terms actually correspond to my training and test errors. And we saw that, okay, well, you know this if I had to summarize my entire discussion, this is the graph that would summarize it. Okay, that is what I was trying to, maybe explain to you, right? So basically we came up with this graph and saw that, okay, high bias low variance regions are not good. Even low bias high variance regions are not good. Okay, what we want is something in between. For that, we said that, okay, why don't we start with a high variance region and keep increasing my bias so that we hit the sweet spot. And, I mean, I hopefully the optimal model also lies here. Okay, the optimal model should hopefully be closed in this region itself. And, though I was not able to calculate my, optimal model, I gave you a machinery. Okay, I gave you a formulation or a way to actually come close to this sweet spot. Okay, start from a big model, a high variance model, uh, lower its complexity, decrease its complexity. Eventually you might be close to your optimal classifier or optimal model. This was the whole idea. Okay, now another question that someone might ask is that, why don't I start from a, low variance region? Okay, and keep increasing the complexity of my model. Well, the answer to that question would be that, you know increasing the complexity of a model is tougher than, decreasing the complexity. For example, so this in this example, it was much easier to, set a set of coefficients to 0. Let's say I started with something like, a10 x raised to 10 plus something 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 a0. Okay, now you're so this is, I hopefully this is the, so this was the area. Or even let's start with a1x plus a0. Okay, so this is the low complexity region that was there in the graph, right? So hopefully this is a1 x naught, like a1 x1 plus a naught. This will lie in this region. Okay, so this region. Okay, now you are saying that increase the complexity of my model. Increasing the complexity would mean that you want to add a x square term, x cube term, x raised to 4 term, and things like that. So let's say you wanted to add the second term a2x square plus a1x1 plus a naught. But now you will have to learn this a2 separately. Now I don't know what this value of a2 is going to be, right? I mean, that is tough. That is tougher to. I mean, I hope you can see the uh, toughness of this problem. Next, you have to add a a3x cube term plus a4x raised to 4 term. How do I come up with these values a4, a3, a2? So it is better to start with something which is already complex and reduce its complexity, and so that hopefully you will get to your sweet spot that you. So let me know if there is any question that you have. Otherwise, maybe I will drink some water. Okay.
Bias and variance is much clearer now. Thanks so much. You explained it very well.
Okay. Thanks. Uh, all right. So maybe when I learned bias variance trade-off for the first time in my bachelor's, it didn't make much sense to me. It was able to make sense in a very intuitive and vague way. Actually, it was I saw some lectures. I said some people said that overfitting and underfitting terms like that. Visually it did make sense, but if something is, well, it was more of something that I understood in a way that okay, uh, I want to minimize two. I generally, how I understood was, I have two loss components. I want to minimize both of them, and that is all regularization is. I didn't see it from this point of view that okay, you are starting from a region which has high variance and moving towards a region which has high bias, and hopefully you will hit the sweet spot. Yeah, yeah, exactly. I mean, it's a cycle that many topics have to be done many times. Yeah. Okay. So this was, more or less the explanation. So I think I took most of the time in this explanation. So next, I want to solve some questions from the assignment. But given that we have less time, maybe I would like to ask you: do you want me to? So maybe there is some question that you want me to solve first. That would be better. So there is the third question. What is this third question? Okay. Okay. Yeah. Any more so that I will note it and just keep solving. Question third, I have noted that, right? So yeah. There is also question eight. So question three, eight, 10. Any more? Okay. Seven. Okay. Please don't fill in the blanks and say one, two, four, five, six, nine. Okay. Okay. Okay, so let's start from third question, maybe. Maybe other people can also post the question number if they have any doubt. Okay, so let's start with third question. Okay, so I have, so it's 7:26. I have time till 8. Okay, fine. So here is the question. Third question. Okay. So basically, what is it? We given our two plots depicting two regularization techniques, which we refer to left plot as A and right plot as B. Okay, choose the correct option. A represents L1 regularization, A represents L2 regularization. Okay, things like that. Fine. So to solve this question, what we need to understand is what is L1 regularization and L2 regularization first. Okay, so L1 regularization. Okay, so I hope I will use this notation. Okay, omega of f or whatever it is. So in L1 regularization uh, for a regression task, let's say, right? So uh, omega of f is quantified as L1 norm of W, okay, L1 norm, okay, and for L2 regularization, omega of f is said to be this thing, L2 norm, okay. So what is L1 norm of W? So W is a vector, okay. Let's say since the given problem is in two dimension, let's say that it is a two-dimensional vector. W1 and W2 is what its values, okay. Now, what is the L1 norm? Okay, so my subscript was at a wrong place. This would be simply absolute value of W1 plus absolute value of W2. Okay, this is what L1 norm is. What would be the L2 norm of it? L2 norm would be, okay, so just I will keep this in bracket because L1 norm is not the vector itself. What would be the L2 norm? L2 norm is what? It is mod of the square root of W1 square plus W2 square, right? Okay. So let me draw the, okay. Okay, so what I will do first is, okay, let us see some contour plots of these things, right? What do I mean by contour plot? So let's say if I say that, so let's start with L2 norm because that is easier. L2 norm, how does it look like? L2 norm is this thing, right? W1 square plus W2 square. Let's say that I fix some value for this. Okay, if I say the L2 norm of W is, let's say, some R. Okay, what would this look like? This would imply that W1 square plus W2 square is R square, right? Okay, someone is asking question 6 as well. Okay, we'll keep this in mind. This is what it would look like. So if I fix a value of the L2 norm, the L2, this is what it would look like, right? So on a W1, W2 plane, so let's say that this is your, so this is your W1, this is your W2. If I fix a R, if I fix a R, what are the feasible W's that I can use? I hope you will agree. Maybe I will try to. Oh, yeah. So I hope you will agree with me that this would be nothing but W. So the points, this thing, right? So I hope you will agree that this thing is equivalent to this thing. That means that all the points on this boundary, right, on the boundary of this circle are feasible points for me. Okay. I hope you will agree that this the points on this the points on boundary of this circle are uh, good enough because they all satisfy this relation, right? Having said that, if I so how would a contour plot for W1 for how would a contour plot for norm of W2 look like? It would look something. So it would look something like this, right? So this is the first axis. It would be concentric circles basically. So this is, let's say, the first circle. This is the second circle. It should have been very concentric, but okay. Pardon my drawing, but nonetheless, something like this, right? This is how for different values of R. So let's say this maybe this was for R1, this was for R2 or R3, and things like that. Now, uh, if you are using a L2 regularization, your overall loss function L tilde will be what? L plus norm of W2, L2 norm of W, right? Whole square of it to be more generic. We want to avoid the square root, but you can see that if I do a square, instead of R, it would become root R here. Things like that. Not a big deal. Okay. Now let's say you have a contour. So this is your contour plot for what? This term, right? Now what is the contour plot for, maybe your actual loss function? The actual loss function might look like something like this, right? So maybe this is uh, this is becoming cluttered. Here I will copy this, take it on next page. Okay. Okay, this maybe this is what the contour for your data set. So the loss function, the first term in the loss function looks like maybe. Okay, something like this. Something like this. I don't know. I just drew something. Okay, so maybe if you start from, let's say this is the point that you start from, okay, and maybe you are decreasing. So you have to reduce both your loss functions, right? So you have to reduce this term as well as this term. What will the optimal value of this term be? The optimal value of this term would be something which has zero norm, right? I mean, the sum of squares can not be lesser than zero. So the optimal value of this second loss function is going to be zero. However, the optimal value of this loss function we don't know. But so adding a regularization term, what it will do is that, so maybe the trajectory would have been something like this, okay. But what adding the regularization term will do, it will say that, okay, since I want to minimize both my loss functions, this has to go in this direction only. Why? Because you want to reach till zero as well, right? I mean, I hope you will understand. I hope you get my point. Since this is the optimal value that I want to reach to, right? This is not the going this path would increase the L2 norm, right? Whereas I want to decrease my L2 norm. The decreasing, so the only way I decrease my loss function as well as my L2 norm is by moving on this path. So hopefully you will agree that something like this is what we will go on. So right, so the second figure that, so this is exactly how the B plot looks like, right? So the B plot should correspond to L2 regularization. Right? Maybe I hope I have convinced you. If I have not, maybe ask questions. Okay. Um, you can just unmute yourself and ask question, or even type things. Okay. Okay. So this was one plot. What is the second plot? The second plot looks okay. Instead of going from plot to answer, let's go from answer to plot. Okay. So what would L1 regularization look like? Okay. So we just saw that sometimes my tab behaves very weirdly. I don't know why. So it has something like this, right? So the first absolute value of the first term plus absolute value of the second term, right? And now let's say I want to now I want to see the contour plot for this function, right? So let's set it to some R, okay? So now there can be various cases, right? What can be the various cases? Maybe W1 and so if I draw my this thing, right, this plane, this is W1, this is W2, these are both positive. This part of the thing is both positive. Here W1 is positive, W2 is negative. Here both are negative, and here one is negative, one is positive, right? This is basic thing. I just wrote it to make things sure. So there can be all these four cases are possible, right? Now let's consider the first case that both of them are positive. So what I'm saying is that W1, W2 are in this uh, quarter of my Cartesian plane. Okay. So in that case, since both of them are already positive, removing the absolute, I can just remove the absolute value, right? So for the absolute value of positive number is the positive number itself. So this will simply become W1 plus W2 is equal to R, right? What would this mean? So I am trying to bring it in the form of y is equal to mx plus c. So this will become W2 is equal to minus W1 plus R, right? Now, so what do we know? We know that it has a negative slope because I have a negative sign here, right? And it cuts the y-axis at plus r. So what would it look like? Maybe it cuts the axis at plus r. So this is plus r, and it has a negative slope. So negative slope of -1. So I hope I will agree that it will look something like this. And since it has a slope of -1, this will also be plus r. Okay. So this is, so just remember that this is the first case. Okay. So this was plus comma plus. What if I take this case? One is positive, says other is negative. That would mean that the first term is positive, so it will just open up as it is, W1. The second term is not positive though, right? So it will like open up with a negative sign, right? So W1 minus W2 is equal to R. So imagine the term is -3, right? So absolute value of -3 is 3, which is minus of -3. This is what I have written, right? So again, keeping it in form of y is equal to mx plus c, this is what w minus w2 is equal to minus w1 plus r. This implies that w2 is equal to w1 minus r, right? So what does this tells us? That it has a positive slope. So it has a +1 here, so positive slope, but it cuts the y-axis at minus r. Okay, so it cuts the axis at, so this is minus r, and it has a positive slope. So positive slope would look something like this. And since the slope is +1, the slope is +1. So I hope you will agree that this is also plus r. So what was the previous one looking like? Previous one was looking something like this. And if you take the other cases, maybe you can do it as a homework or something, practice. You will see that this is what the entire thing would look like, right? So uh, just to complete my thoughts, I'm making that diagram again. This is the first axis, this is the second axis. Just making things. So this was the thing that we just saw, right? So, okay, so this was plus r minus r plus r minus r, right? So I hope you will agree that you can similarly make for different value of r's, you can make something like this, right? Things like that, some inside also. Okay, I hope you will agree. So it is actually a rhombus now. And can I copy this thing? That would be very great. Copy, and if I'm able to paste it, okay, thank God. Right, so something like this. So if I start from here, now again, what do we want? We want to minimize both the loss function, the original loss function, and the L1 norm as well. So what is the, again, what is the minimum value of L1 norm? So the minimum value of this absolute value can be 0. Absolute values are always uh, 0 or greater than 0, right? It cannot be minus negative thing. Okay, so this can be 0. The minimum value that this can take is 0. This value can be at least, so this, the minimum value of the second term will also be 0. So L1 norm has a minimum value of 0. Okay, so this is the minimum value that it can take, and here you are right. Okay, so now there can be, you can take this path and go like this can be one trajectory. You can also go like this, something like this. So since these are level curves, both of them are equivalent, because level curve means that all these values are same, all these values are same, all these values are same. So there is no, though you cannot differentiate between them. However, since you are now saying that I also want to minimize my L1 now, what you will do is, you will have to take a path which looks something like this. Would you agree? Because this is the only path, not the only path, but this is one of the path which actually also reduces your L1 now. Whereas these path and these path were actually increasing your L1 now, because they were going away from 0, right? Whereas this path is going towards 0, so it is actually decreasing your L1 norm as well. So I hope you will agree that this is your A plot, right? As shown. So the correct options would be that A represents L1 regularization, and B represents L2 regularization. So I hope this was clear. If not, ask questions. Okay. Okay. So the next question that is demanded is sixth one. Okay. What is the sixth question? Okay, I am also closing in on time. So sixth question is you are given a table. Okay. You are okay. Okay. So this is epochs, uh, training error, and this is a validation error. Okay. What is it? One, two, three, 4, 5, 6. Training error is given to be 4, 3.5. Okay, it is decreasing. 3, okay, it has decreased further. 2.2, okay, still decreasing. 2, okay, now. Okay, it is decreasing. The training error is decreasing with epochs. But is that something we should be very maybe surprised with? Well, no, right? Because training error is something that you can always minimize because just if an algorithm is even memorizing the data, it will reduce the error, right? So nothing great with this, right? Training error is decreasing should not be surprising to us. What should be surprising though is the validation error decreasing. So let us look at the validation error. So 5, okay. 3.8, good, it is decreasing. 3.3, okay, nice, still decreasing. 3.6, oh well, now it didn't decrease, okay. Instead it has increased. So this is alarming, okay. Next time again 3.6, well again it didn't decrease, it remained constant. And next time it came out to be 3.4, oh, now it decreased, okay. So this is basically the idea, right? So what I was saying, right, the training error was decreasing, the validation was decreasing, but it again increased, came constant, and did something like this, okay. So I hope the picture is clear. This is how the plots would have looked like if you had plotted them, okay.
No, they have sort of also correlated with, I mean, mentioned patience parameter equal to 2.
Yeah. I'm just coming to that. I'm coming to the early stopping part of it. Okay. So apart from this, what is given to us, as Mona pointed out, was that we are given a patience parameter, which is given to be 2. Okay. And so this there is a regularization strategy called uh, early stopping. How does early stopping work? What it does is that it keeps track of your validation error. Okay. So here is how it goes. So you are saying your algorithm that okay, keep training. Okay, I know my training error is going to decrease, so keep training. However, also look at the validation error. Make sure that the validation error is also decreasing. If it is not decreasing, wait for some time. I mean, let it go on. But if you have waited sufficiently large enough, I mean, if you have spent a lot of time in waiting, now you just stop the algorithm, okay. This is what early stopping says. So I mean, for a visual from a visual point of view, you are saying that okay, the training error is going down and down and down, okay. But you are saying that okay, also keep track of your validation error. Validation error is decreasing, fine. Till now your algorithm is fine, okay. But now it starts to increase, maybe do something weird and things like that, okay, something like this. What early stopping does is that it notes the point where you started to increase your error, okay. So this was the point where you started to increase your error, right? It waits for some p number of epochs, which is your patience parameter, okay, which is 2. So in this case, it will wait for 2 epochs. It saw so it waited for the one more epoch. It saw that okay, the error has actually increased. It has not decreased, okay. But you are saying that okay, keep patience, wait for one more epoch. It is saying that okay, fine, I am waiting for one more epoch. Well, it is still not so the error has still not decreased, it has in fact increased or something, right? Now you say that okay, you have a lot of patience, and now you have waited enough, just end the algorithm. So what it will do is that it will take this but it will take this particular point, okay, the value of the parameters at this particular point, and whatever the value is, it will output that, okay, right? So I hope the early stop died. So I am not doing a formal thing. I am just giving an intuition because we have less time. So I hope the idea was clear. So in this case, in this case, let us see what will happen. Okay. So we got from 5 to 3.8. Okay, that is fine. We went from 3.8 to 3.2, 3.3. So still the error is decreasing, but now it has increased to 3.6. So this is the red flag. Okay, the algorithm is now alert that the error is increasing, but the patience parameter is 2. So it has waited for one epoch, it has to wait for one more epoch. Okay, so if it waits for one more epoch and it sees that okay, it is still 3.6, it has not decreased. Now it says that okay, I have waited enough. What I will do is I will terminate the this entire network at this point. Okay, this point. So whatever the value of the parameters will be at third epoch, I will output that. Okay. So what is the answer? So when will the training stop? Okay. Okay. So it is saying that at what epoch it will stop, right? Okay. Yeah. So it will output the value of the parameter at third epoch. Okay. But I mean, eventually it has waited till fifth epoch, right? I mean, it has waited for 3 plus 2. Since the patient's parameter was 2, it has waited for two more epochs. So fifth epoch. After fifth epoch, it will stop. So this is where it terminates, right? Okay, right. So this it will end after fifth epoch 5, right?
What I
I
didn't
hope
understand
it is.
was, what I didn't
Yeah,
understand was you just said that it will get alert once its error decreases, the validation error decreases, so that sorry, increases. So the validation
yeah.
error is only you get alerted at epochs 4. So
Mhm.
after epochs 4, that means. So should it not be
Yeah.
till epoch 6? Because after
No,
epoch 4, you have to have two, another one.
right. Yeah. So by the time it got, you are right in saying that it got alerted at this epoch, right? But by then it has already waited for a one epoch, right? I mean, this is how you count that the
Okay.
time, the epoch at which you are alerted that okay, see the
That's the
validation is
first
okay,
epoch,
error
and
is
then wait for as many
yeah.
more. Okay, fine.
Yeah, so
Thank you.
now you have to count from three itself. So from here you count two epochs, so fifth epoch will be the answer. Yeah. So this is the this is how you count.
Okay, fine.
Okay, so okay, let me just cut down the questions that we have done. Three is done. Right now we solved sixth, I guess. Seventh one. What time is remaining? 7:50. Okay, fine.
You
Then
can skip 7 and then maybe explain 8 then. 8, 10.
okay, so these two, right? So okay, fine. Let's go to eighth. Eighth question says that let me come down. So here is the eighth question. What it is saying is that you have some network. Let me quickly draw it. Three layers here, three layers in first hidden row, again three hidden neurons here, and three output layers. Okay, fine. How many thinned network can be formed from? So I hope you know what a thinned network is. By the thinned network, what we mean is that so look at it as a graph. So there are multiple connections here, things like that. Okay, so you can complete the rest of the connections and things like that, right? So this is a graph. I mean, from a computer science and data structure perspective, this is nothing but a graph, right? In a graph, there can be multiple subgraphs, right? So the thinned graph, so thinned network is nothing but it is asking you that how many subgraph can you construct from this big graph? Okay, this is the ultimate question that it is asking. Well, now since it is a neural network, okay, since it is a neural network, you cannot go away with this first and last layer, right? Because this is the input layer, this is the output layer. You will have to give some input, and you will have to uh, you will get some output. You cannot say that okay, mean, basically this is something that is coming from dropouts. Okay, in a neural network you cannot say that, okay, not this time I will only give you two inputs, next time I will give you only one input, and another time I will give you all the three inputs. You cannot say anything like that. Same with the outputs. You cannot say the network that, okay, just output two of them, just output three of them, or things like that. So these two layers, maybe I will circle them. So these two layers I cannot do anything with them. Okay. um, just a second. I think there's some issue with this thing. Uh, okay, I'm not able to see you guys for some reason. I don't know. Okay, fine. Yeah, now I'm able to see. Okay, fine. Yeah. So what I was saying is that you cannot go away with the input and output layer. So input and output layers have to be there. Okay. However, you can, let go of some of the hidden layers. Okay. So, uh, uh, okay, so fine. So how many subgraphs can I make from this? So here is how you will do it. So each of this node, okay, this node, or this. Let's choose one of the nodes. In each selection, I can either keep it or I cannot keep it. Okay. So it has two choices, right? Either keep it or don't keep it, right? Similarly, this node has two choices. Either I will keep this node or I will remove it. Okay. Similarly, this node has again two choices. Either I will keep it or I will remove it. Same thing goes for this node, and this node as well. So two choices, again two choices, right? So if I see what are all the possible combinations that I can make from a very basic combinatorics, and this is basically a counting problem. I have to, so the total number of ways would be 2 times 2 times 2 for the first layer times, so this was the first layer, first hidden layer, 2 times 2 times 2. This was for the second layer. So this is 2 cube into 2 cube, 2 raised to 6, 2 raised to 6. I think it's 8, 8, 8 is a 64, right? So the answer should be 64, right? So this would be the answer. Uh, if you have any doubt, you can ask. Okay. If not, we will move forward. Okay. So this was what? This was the eighth question, right? So let me cancel that off. So 10th question is remaining. What is the 10th question? Sorry. Okay. Okay. So here is the 10th question. The 10th question is saying that we have trained four models in the same data set. Okay. So let us make our mind heads clear. Okay. The data set is same. Okay. But we have trained four models. Okay. So let's say we have been given some model one, two, three, four. Okay. Fine. The training and validation loss for the models are listed below. Okay. So this is like training error again, and this is some validation error. Okay. So I hope you know what is training error and what is validation error. I won't explain it. If you don't know, ask me. I will explain it to you. So what is it? What is given to us? This is 0.3. Okay. This error has this model. The first model has bit low, has very less training error. The second model has a training error of 0.9. Oh, some a bit more. Okay. So third one has a zero point 0.5 training error. All right. Fine. 1.9. Okay. So I mean, I hope you will agree with me that giving these errors doesn't make any sense. Okay. I mean, I can make my training error as small as possible with a sufficiently large neural network or something like that. Okay. What I actually need to look at is the validation error. So what is the validation error? This is 1.7, right? This is 1.1. This is 0.7. This is 2.3. All right. So we are asked that which model should we choose to get the best test data, best result on test data set, right? So if you remember the graph that I just made, okay, so this is your training error that can go as low as possible, right? Then you have something called validation error, right? Something like this. Just let me make this. Okay. The best choice of a model is when you are hitting this sweet spot. Okay. This is the validation error. Okay. This is the training error. So don't confuse it with that uh, bias variance trade-off. So this is, I mean, you can compare it. I mean, like, it is actually the same thing, but just saying that can get confused. Okay, so this is the sweet spot that you want. At the sweet spot, we know that validation error is close to your training error, right? I mean, both of these things are very close to each other. So whichever model gives me the least difference between validation error and training error, I will choose that model. I hope you will agree with me, right? That is the model that we should use. So I will. So let's make a difference table here. Okay, what is the difference here? 0.3 and 1.7. So it has a low test error, but high validation error. Where would this model lie? Low test error and high validation error. I hope you will agree that it will lie I mean, it will lie somewhere here, right? I mean, so it should lie in this region, right? And somewhere here because it has a low training error, but the validation error is very high. So I hopefully something like this. Okay. So this is M1. Okay. What is the error of it? It's 1.4. Okay. So let's look at the second model. This has a error of what? 0.2. Okay. 0.2, fine. So it also has some training error which is more than this one. Okay, so a training error which is more than this one. So a bit here maybe, but it still has a what? It has a high validation error, right? 1.1 something. But the difference is just zero point 0.2. So maybe somewhere here, perhaps, yeah, something like this, right? I hope you will agree that training error is bit high, right? So I hope you will see that the training error here. I mean that there is some difference here, right? So the training error is more. The validation error is something, but this difference is what 0.2 is what we are seeing. 0.2. This error was what 1.4, right? Yeah. So this is M2. Okay. What is the third model? It has a training error even less, 0.5. Okay. Okay. So have I made any mistake? Because it should lie somewhere uh, zero point 0.9 and zero point 0.5. Okay, I think I made a mistake. Oh, so I mean I didn't make a mistake, but visually saying this is not where M2 should be. It should be somewhere here, right? Why? Because I mean because I want to add a W, so I want to add the M3, the third model. I think this is a better way to put M2. Okay, this is M2. It has a training error which has which is larger than this one. So and but it has the difference between the validation error and this training error is less. So this is what this is like around point 2. Okay, so this is just 0.2. Fine. So now I have a model which is M3. M3 has a training error of zero point 0.5. So it is between M2 and M3, right? It is between M2 and M3. So I mean maybe somewhere here perhaps. Yeah. Uh, so I hope if this is maybe if this training error is what zero point 0.3, this is zero point 0.9. I hope it is believable that okay this will be something zero point 0.5, right? But it is also given to us that it has some validation error and that validation error is less than both of them. So whatever this was what 1.1, this was what 1.7, and but this is something like 0.7, and hence the difference here is also what difference here is 0.2, right? So here also the difference is 0.2, but it is lying somewhere in middle. Okay. All right. Where is the fourth model? For the fourth model, training error is also high and validation error is also high. So I hope you will agree that that those kind of models will come here, where you have a high training error. So the training error here is what, 1.9. So more than 0.9, 0.5 and zero point 0.3. However, it also has a high validation error, which is what, like 2.3, something like this. So this is where M4 will stand, right? So amongst these four model, can you tell me which model I should choose? I mean, so what I have done is that I have taken the information that was given to me. I have placed them in in the graph which I am comfortable with. Okay, that is all I have done. So I hope you will agree that this M3 model, I didn't label it M3 model. This is the model which is close to our sweet spot, right? Because all the other models where this is where so this is the region where you have high bias and low variance. This is the region where you have what, high variance and low bias. But this is the sweet spot that I wanted. It is closer to the sweet spot that I wanted, right? So hopefully you will agree that the third model is the one that I want. Okay. So having said that, so maybe I will just write it down. M3 is the winner. Okay. Yeah. So going back, uh, so I think this one is also done. Maybe you said I can skip seventh one, so I will just skip it, and we are also out of time. So I hope this was clear to you. If not, please let me know. If you have any other comments, I mean, I will stop with this. Okay. I mean, I am also exhausted. 2 hours is a long time. So, having said that, if you have any doubts, if anything was not clear, you can ask them. Or if you have any other comments, you can let me know of that as well. Okay. So, okay, right. So, yeah. So with this, I think we will close this session. Yeah. Any question?
When we'll have a next session?
So this session is held regularly on Fridays. Okay.
Okay,
Friday 6 to 8. Okay. So
okay,
this
got it,
is the time that we have fixed
got it.
for these sessions.
Thank you. Have a good night.
Yeah. Yeah. Okay. So so maybe if you don't have any questions, we will stop here, and we will let's meet in next session maybe. Okay. So with this, thank you, thanks a lot. Uh, 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 have a nice evening and good night. Okay, I will end the meeting now.
Piyush, hello.
Yeah, yeah.
Yeah. I have, few questions related to my work. Can I have, your mail ID or any number so that I can ask you?
Uh, okay. So maybe you can mail me on this. So I am putting it on in this chat box. Okay.
Yeah.
Yeah.
Chat,
Right. So, if you have any doubts or anything that you would like to discuss, you can mail me here. All right. So with this, let's. So should we end this meeting if you don't have anything else to ask? Yeah.
Yes, sure. Thanks so much.
thank you.
Yeah. Okay. Okay. Bye. Thank you. Bye.